In mathematics, a topological space is called separable if it contains a countable, dense subset, that is, there exists a sequence x n equals 1 infinity \displaystyle x underscore n \underscore n equals 1 caret infty of elements of the space such that every non-empty open subset of the space contains at least one element of the sequence. Like the other axioms of countability, separability is a limitation on size, not necessarily in terms of cardinality, though, in the presence of the Hausdorff axiom, this does turn out to be the case, see below, but in a more subtle topological sense. In particular, every continuous function on a separable space whose image is a subset of a Hausdorff space is determined by its values on the countable dense subset. Contrast separability with the related notion of second countability, which is in general stronger but equivalent on the class of metrizable spaces. Any topological space that is itself finite or countably infinite is separable, for the whole space is a countable dense subset of itself. An important example of an uncountable separable space is the real line, in which the rational numbers form a countable dense subset. Similarly, the set of all vectors car 1 car n set membership symbol car n \displaystyle r underscore 1 comma \lots r underscore n \n math bar caret n, in which car I \displaystyle r underscore I is rational for all I is a countable dense subset of car n \displaystyle math bar caret n. So for every n \displaystyle n, the n \displaystyle n dimensional Euclidean space is separable. A simple example of a space that is not separable is a discrete space of uncountable cardinality. Further examples are given below. Any second countable space is separable if u n \displaystyle u underscore n is a countable base, choosing any x n set membership symbol u n \displaystyle x underscore n n u underscore n from the nonempty u n \displaystyle u underscore n gives a countable dense subset. Conversely, a metrizable space is separable if and only if it is second countable, which is the case if and only if it is Lindelof. To further compare these two properties, an arbitrary subspace of a second countable space is second countable. Subspaces of separable spaces need not be separable, see below. Any continuous image of a separable space is separable, Willard 1970, th 16.4a. Even a quotient of a second countable space need not be second countable. A product of at most continuum many separable spaces is separable, Willard 1970, p. 109, th 16.4c. A countable product of second countable spaces is second countable, but an uncountable product of second countable spaces need not even be first countable. We can construct an example of a separable topological space that is not second countable. Consider any uncountable set x \displaystyle x. Pick some x 0 set membership symbol x \displaystyle x underscore 0 n x, and define the topology to be the collection of all sets that contain x 0 \displaystyle x underscore 0 or are empty. Then, the closure of x 0 \displaystyle x underscore 0 is the whole space. X \displaystyle x is the smallest closed set containing x 0 \displaystyle x underscore 0, but every set of the form x 0 x \displaystyle x underscore 0 x is open. Therefore, the space is separable, but there cannot be a countable base. The property of separability does not in and of itself give any limitations on the cardinality of a topological space. Any set endowed with the trivial topology is separable, as well as second countable. quasi-compact, and connected. The trouble with the trivial topology is its pure separation properties. Its Kolmogorov quotient is the one-point space. A first countable, separable Hausdorff space, in particular, a separable metric space, has at most the continuum cardinality. C. \displaystyle \mathfrac. In such a space, closure is determined by limits of sequences, and any convergent sequence has at most one limit, so there is a surjective mat from the set of convergent sequences with values in the countable dense subset to the points of x \displaystyle x. A separable Hausdorff space has cardinality at most 2 c \displaystyle 2 \mathfrac, where c \displaystyle \mathfrac is the cardinality of the continuum. For this closure is characterized in terms of limits of filter bases, if while subset symbol x \displaystyle y subset x and z set membership symbol x \displaystyle z and x, then z set membership symbol while \displaystyle z and overline y, if and only if there exists a filter base b \displaystyle mathcal b consisting of subsets of while \displaystyle y that converges to z \displaystyle z. The cardinality of the set s while \displaystyle s while of such filter bases is at most 2 while \displaystyle 2 y. Moreover, in a Hausdorff space, there is at most one limit to every filter base. Therefore, there is a surjection s while x \displaystyle s y right arrow x when while equals x \displaystyle overline y equals x. The same arguments establish a more general result. Suppose that a Hausdorff topological space x \displaystyle x contains a dense subset of cardinality kappa \displaystyle kappa, then x \displaystyle x has cardinality at most 2 kappa \displaystyle 2 kappa, and cardinality at most 2 kappa \displaystyle 2 kappa if it is first countable. The product of at most continuum many separable spaces is a separable space. Willard 1970, p. 109, th 16.4c. In particular, the space bar \displaystyle mathbar of all functions from the real line to itself, endowed with the product topology, is a separable Hausdorff space of cardinality 2 c \displaystyle 2 mathfrac. More generally, if kappa \displaystyle kappa is any infinite cardinal, then a product of at most 2 kappa \displaystyle 2 kappa spaces with dense subsets of size at most kappa \displaystyle kappa has itself a dense subset of size at most kappa \displaystyle kappa. Hewitt-Marchevsky-Pondixery theorem. Separability is especially important in numerical analysis and constructive mathematics, since many theorems that can be proved for non-separable spaces have constructive proofs only for separable spaces. Such constructive proofs can be turned into algorithms for use in numerical analysis, and they are the only sorts of proofs acceptable in constructive analysis. A famous example of a theorem of this sort is the Hahn-Banach theorem. Every compact metric space, or metrizable space, is separable. Any topological space that is the union of a countable number of separable subspaces is separable. Together, These first two examples give a different proof that n \displaystyle n dimensional Euclidean space is separable. The space C K \displaystyle C K of all continuous functions from a compact subset K subset symbol R \displaystyle K \subsetec \mathbar to the real line R \displaystyle \mathbar is separable. The Leibniz spaces L P X mu \displaystyle L caret P \left X \move \right over a separable measure space X M mu \displaystyle left Langley X math cal M comma move right wrangle are separable for any 1 less than or equal to P infinity \displaystyle 1 like P infty. The space C 0 1 \displaystyle C 0 1 of continuous real-valued functions on the unit interval 0 1 \displaystyle 0 1 with the metric of uniform convergence is a separable space, since it follows from the Weierstrass approximation theorem that the set Q X \displaystyle math QX of polynomials in one variable with rational coefficients is a countable dense subset of C 0 1 \displaystyle C 0 1. The Banach-Mazur theorem asserts that any separable Banach space is asymmetrically isomorphic to a closed linear subspace of C 0 1 \displaystyle C 0 1. A Hilbert space is separable if and only if it has a countable orthonormal basis. It follows that any separable, infinite-dimensional Hilbert space is isometric to the space 2 \displaystyle L caret 2 of square-summable sequences. An example of a separable space that is not second countable is the Sorgenfrey line S \displaystyle math the set of real numbers equipped with the lower limit topology. A separable sigma algebra is a sigma algebra F \displaystyle math cal F. That is a separable space when considered as a metric space with metric rows K B equals mu K B \displaystyle row A B equals moon A triangle B 4 K B set membership symbol F \displaystyle AB and math cal F and a given measure mu \displaystyle moon and width \displaystyle triangle being the symmetric difference operator. The first uncountable ordinal omega 1 \displaystyle omega underscore 1 equipped with its natural order topology is not separable. The Banach space infinity \displaystyle L caret infty of all bounded real sequences with the supremum norm is not separable. The same holds for L infinity \displaystyle L caret infty. The Banach space of functions of bounded variation is not separable. Note, however, that this space has very important applications in mathematics, physics, and engineering. A subspace of a separable space need not be separable. See the Sorgenfrey plane in the Moore plane. But every open subspace of a separable space is separable. Willard 1970, th 16.4b. Also, every subspace of a separable metric space is separable. In fact, every topological space is a subspace of a separable space of the same cardinality. A construction adding at most countably many points is given in Sierpinski 1952, p. 49. If the space was a Hausdorff space, then the space constructed that it embeds into is also a Hausdorff space. The set of all real-valued continuous functions on a separable space has a cardinality less than or equal to C \displaystyle \mathfrak C. This follows since such functions are determined by their values on dense subsets. From the above property, one can deduce the following: if X is a separable space having an uncountable closed discrete subspace, then X cannot be normal. This shows that the Sorgen-Frey plane is not normal. For a compact Hausdorff space X, the following are equivalent I. X is second countable. 2. The space C X car \displaystyle \mathcal C X \mathbar of continuous real-valued functions on X with a supremum norm is separable. 3. X is metrizable. Every separable metric space is homeomorphic to a subset of the Hilbert cube. This is established in the proof of the Urisan metrization theorem. Every separable metric space is isometric to a subset of the non-separable Banach space L infinity of all bounded real sequences with a supremum norm. This is known as the Frechet embedding. Heinen 2003. Every separable metric space is isometric to a subset of C 0,1, the separable Banach space of continuous functions 0,1 R, with the supremum norm. This is due to Stefan Banach. Heinen 2003. Every separable metric space is isometric to a subset of the Urisan universal space. For non-separable spaces, a metric space of density equal to an infinite cardinal alpha is isometric to a subspace of C 0,1 alpha R, the space of real continuous functions on the product of alpha copies of the unit interval. Kleiber 1969.